Hi, welcome to the week 7 problem solving session. I hope I'm audible to you. Can you just write in the chat in case I'm audible to you? Hi, Aparna, am I audible? All right, thank you. I'll just wait till about 6:10 so that if there are other people to join, they can join and then I'll start with this week. Okay? Hi, I hope I'm audible to you. Am I audible? Can you write the answer in the chat? Devaki, are you there in the call?
Of course, I'm in the call.
Am I audible now? All right, thank you. So we'll start with week seven questions. So these questions will be similar to the ones you had in your assignment seven, and as we move forward, we'll solve any doubts that you had. Okay. So let's start with the first question, and just tell me what you think the answer is. You can just write it in the chat. Okay. So the first question is, in batch sterilization, it is difficult to get an ideal temperature time profile. It's a simple theory related question. Do you think it's true or false? You can just write the answer in the chat. Alright. The answer is in fact true. It is difficult to get an ideal temperature profile when you do batch sterilization versus when you do a continuous sterilization. So moving on to question number two, um, with the increase of superficial air velocity, the collection efficiency of impaction decreases, whereas collection efficiency of diffusion increases. Is it true or false? I hope I'm audible to you. You can just type your response in the chat box. Alright. Then the answer to this question is false. So it is not true that when you increase the superficial air velocity when you're charging a bioreactor, uh, sorry, when uh, when you're charging a bioreactor, the collection efficiency of impaction decreases, whereas the collection efficiency of diffusion increases. So that is not true. When you increase the air velocity, the collection efficiency of impaction actually increases, and the collection efficiency of diffusion decreases. When the air velocity is less, that is when you have a efficiency of impaction which will decrease, and efficiency of collection efficiency of diffusion will increase. Alright. So let's move on to question number 3. In case of ungassed Newtonian fluid, power required for laminar flow is independent of the viscosity of the fluid with proportion to the fluid density. Is that true or false? The answer is false. So when you have ungassed Newtonian fluids, right? Newtonian fluids in this case, over time and over different pressures, their viscosity does not change as such. Okay. Uh, so in case of ungassed Newtonian fluids, the power required for laminar flow is, is um, should I go back to the first two questions, or do you have a specific doubt with week number 7? Right, I'll just continue. So, when you take the case of ungassed Newtonian fluids, right, the power required for laminar flow is dependent on the viscosity of the fluid. Alright, but when it is gas Newtonian fluid, the power required for laminar flow is independent of the viscosity and proportional to the fluid density. So, in this case, this is false. So, the next question will be, a successful scale-up requires which of these following options? Geometrical similarity only, dynamic similarity only, or both geometrical and dynamic similarity. In this case of species, you have a operation that you have standardized and you want to scale it up. So do you only scale up the operation geometrically, like whatever dimensions of the vessel you had, do you scale that up to the required final value of the product you require? Or do you scale up the dynamic similarity? In this case, things like speed of the impeller, flow rate, or do you do both? So, what do you think the answer is? So, the answer in this case is both geometric and dynamic similarity. For you to have a successful scale up, you have to, you know, uh, make sure that the geometric and the dynamic system that you had made is similar to when you scale it up to a larger vessel, right? Okay, question number 5. Uh, Power number in a bioreactor is constant when Reynolds number is lesser than 10,000 or greater than 10,000. Just think about what power number and what Reynolds number in this case means, and a few basics of the theory that we studied. So the answer to this is greater than 10,000. So when Reynolds number is greater than 10,000, the flow reaches turbulent flow, right? And at that point, power number is constant. Okay. So question number 6. This is a numerical type. So a large scale bioreactor with 10,000 liters of complex medium containing 10 to the power 4 spores per liter is being sterilized. The del factor value for the system is 15, and using the following information, which is gas constant and the temperature, you have to determine the probability of successful sterilization. Okay, alright. So let's start by figuring out what the total number of spores, that is N naught, is. So you have 10 to the power 4 spores per liter, and you have 10,000 liters, right? So the total number of spores is 10 to the power 8 spores. Okay, and del factor is 15, and you know del factor is equal to the death rate constant into time, right? Now you are assuming that all the viable cells or spores are identical, okay? And the probability of extinction of the total population is, in this case, P naught T is equal to 1 minus Pt, and the entire thing to the power of N naught, which is the total number of spores, okay? Where Pt is the probability that an individual will still be viable at time t, okay? And N naught is the number of individuals initially present. You are assuming that the system is a first order death model. So, and Pt is equal to e to the power k dt. Hence, Pt will be p naught t will be equal to 1 minus, since Pt you know is equal to e to the power minus k dt, and the total, you have this total value will be to the power of n naught, right? So you know the value of E, you know the value of KD, and you know the value of T and N naught, right? So P naught T will be equal to 1 minus E to the power of minus KDT, and you know from here that KDT is 15, which is the del factor, into 10 to the power 8. Okay, so you get 5.18 into 10 to the power minus 14, which is the probability of extinction of force, which is also the probability of successful sterilization. Okay. Now the second question is to determine the probability of unsuccessful sterilization. So you know that the total probability will be 1, right? So 1 minus the probability of successful sterilization will give you the probability of unsuccessful sterilization. So if you subtract 5.18 into 10 to the power minus 14, which is the answer you got here, from 1, you will get the probability of successful sterilization, which is nearly equal to 1, because this value is very, very, very small, right? So there is a high probability of uh, successful, there is a higher probability of unsuccessful sterilization. Alright. So the next question is another numerical. Media is to be batch sterilized in a 200-liter fermenter before it is used to grow microorganisms, using 0.001 as the probability of a unsuccessful sterilization. Okay. That means there is a very less probability of an unsuccessful sterilization. Here, in this case, the probability of success was very low. Here, the probability of success was high. You have to ignore the heat up and cool down, and the information given is for Bacillus stereothermophilus spores. Okay. Uh, so the spore concentration is 1 to 10 to the power 8 spores per liter. E is given, A is given, gas constant is given, and temperature is given. Okay. So according to, so you have to determine the value of Kd, the rate constant of death, at 121 degrees Celsius. Okay. So according to the Arrhenius equation, Kd is equal to A uh, E in to the power of capital E by RT, right? So in this case, you have been given the value of A, of capital E, of pore concentration, and the temperature conversion factor too, right? So A is 1 into 10 to the power 36.2 per minute. Then capital E is 67.7 into 10 to the power 3, because here it's given to you in kilocals, right? So you have to convert that kilocal to cal. So you have a conversion factor of 10 to the power 3, and you divide this by R, which is 1.97 into the temperature. So at 121 degrees, the conversion is 121 plus 273 to get it in Kelvin. Okay. So once you calculate that, you will get the answer as 0.0441 per minute. Now you have to convert this per minute into hours, because the A value given to you was in minutes, so the answer you have gotten also is per minute. Okay. So to convert that into per hour, you have to multiply it by 60. Okay, because it's per hour. So you get 2.64 per hour. Okay. So question number 8 is, sterilization is being carried out in a 1000 dm cube pilot scale vessel. The media contains 10 to the power 6 organisms per centimeter cube, and the probability of unsuccessful sterilization is given as 1 in 1000. Okay. So, so you have to determine the del factor for this probability of contamination. So let's see. The number of viable cells at the start of sterilization, which is N1, is equal to 10 to the power 6. That is what is given. Okay. Into 1000 dm cube, which is also given, and you have to convert this dm cube into centimeter cube, right? So you multiply it by 1000. Okay, because 1 dm is equal to 1 cm, right? So you get the initial number of cells and the number of viable cells at the end of sterilization. N2 is 1 per 1000 organisms. Okay, so that is 10 to the power minus 3. So you know del factor is equal to Kd into T. Okay, and that is equal to natural log of N1 by N2, which gives you natural log of 10 to the power 6 into 10 to the power 3 into 10 to the power 3 divided by 10 to the power minus 3. So what you get is 34.5. So that is the del factor for this probability of contamination. So let's move on. During scale up, a 10,000 dm³ vessel is being used with the same medium as in the previous part. Okay. So you have to determine the del factor for the large vessel if the same probability of contamination is required. Okay. So after scale up, the number of viable cells at the start of the sterilization is this. Okay. Okay. So here you had taken the number of organisms remains the same here also, but the volume of the vessel changes. Since it was a 1000 dm cube vessel, that is what is written here, but now it is a 10,000 dm cube vessel, right? So that is what is written here into 1000 again for conversion. Okay, so the number of viable cells at the end of sterilization is again the same, so that is 10 to the power minus 3. So again, if you take ln, you will get a dilution, a del factor of 36.8. Okay, so it has increased from 34.5 to 36.8 with the increase in the size of the vessel. Okay, so let's move on to question number 9. So the media used for a bioprocess is contaminated with single cells with similar thermal response characteristics. It has been observed that by maintaining the media at 60 degrees Celsius for 15 minutes, 65% of the cells become non-viable. Now you have to determine the decimal reduction time. So you know that the decimal reduction time is equal to 2.303 divided by the rate constant of death, right? You also know that for a first order reaction, the rate constant is given by 2.303 by T log 10 of x v naught by x v. This is the initial number of cells, this is the final number of cells, right? So in this case, you for you to figure out the decimal, reduction time, you need to know KD value. So you will get KD by this formula. So you know time, which is 15 minutes is equal to 900 seconds. You know the initial amount of cells we will consider as 100%, and you know the final amount of cells since 65% has been reduced, so you are left with 35%, right? So therefore KD is equal to 2.303 divided by 900 log 10 of 100 by 35. So you get the KD value as 0.00117. Therefore, the value of D will become 2.303 divided by 0.00117. So D is 1968.38 seconds, which if you convert it to minutes by dividing it by 60, you will get 32.80 minutes. So the decimal reduction time is 32.80 minutes. Alright, that's all for today. These questions would have been similar and helpful for you to solve um, week 7, and I hope you have cleared any doubts regarding the assignment number 7 with these. audible to you? Are you able to hear me?
Good evening, ma'am.
Yeah. Okay. So, do you want me to go through all of the questions, or do you have a particular doubt with assignment number 7?
No, ma'am.
You don't have a doubt, so I'll just go through the questions. There are a few which are similar to the ones you had in assignment 7, and there are a few different ones too. Okay.
Okay, okay, ma'am.
All right. So just write the answer that you think is true for uh, the questions. Okay. So that's all. So let's move on to the first question. So in batch sterilization, it is difficult to get ideal temperature time profile. Do you think it's true or false? Just write it in the chat. Whatever you think the answer is. So this is in comparison to when you're doing a continuous sterilization, like you would have studied in the last week, right? So in this case, when you're doing a batch sterilization, is it difficult to get ideal temperature time profile? So it's a true or false sort of question, which just guess as to what it could be. Doesn't need to be right or wrong as such. Alright, since I don't see an answer in the chat, I'll just move on. It is in fact true. So when you're doing a continuous sterilization, it's easier to get ideal temperature versus time profile. But when you're doing a batch sterilization, it's much more difficult. So in case you don't have a doubt, let's move on to question number 2. Uh,
Okay,
Alright. So with the increase of superficial air velocity, the collection efficiency of impaction decreases, whereas collection efficiency of diffusion increases. And this is again a true or false question. In this case, what we're talking about is when you're sparging air, right? And you're sparging the air, and it's a filtered air. So the air is being filtered as it is being sparged. So in that filter, the collection efficiency of impaction and the collection efficiency of diffusion is what is being talked about with respect to the superficial air velocity, which is the velocity of air that you are pumping in, right? So is it a true or false question? Uh, do you have an idea of what the answer is? Whatever you think is the correct answer, you can write it in the chat. So for this, you will have to remember a little theory about what is collection efficiency of impaction and what is collection efficiency of diffusion. Alright. So the answer to this is that it's false. So this statement is not true. And the true statement would be when you increase the superficial air velocity, the collection efficiency of impaction is what is being increased, while the collection efficiency of diffusion decreases. Alright. So let's move on to question number 3. Uh, In case of ungassed Newtonian fluid, the power required for laminar flow is independent of the viscosity of the fluid but proportional to the fluid density. This is again a true or false question. So a Newtonian fluid will be a fluid which is not affected by uh, which the viscosity is not affected by the shear stress, that is shear rate or shear stress being faced by the fluid. So the answer to this would be false. So, in case of ungassed Newtonian fluid, the power required for laminar flow is dependent on the viscosity. But once you have gas, not ungassed, but gas Newtonian fluid, this statement becomes true. The power required would be equal to, uh, would be proportional to the fluid density, and would be independent of the viscosity of the fluid. But in this case, since we're talking about ungassed Newtonian fluid, the answer is false. So let's move on to question number 4. A successful scale up, which in this case means you have a small setup that you have standardized and you need to scale it up to a higher volume or a higher product use. Uh, you require uh, a geometric similarity to your standardized system, a dynamic similarity, or both. So the answer in this case would be both geometric and dynamic similarity. You have to follow the geometry of the bioreactor system that you had in a smaller scale when you go to a bigger scale, but you also have to make sure that it's dynamically similar with respect to flow rate, with respect to intended speed, and the ratio of different factors. So let's move on to question number 5. Power number in a bioreactor is constant when Reynolds number is lesser than 10,000 or greater than 10,000. So the answer to this would be greater than 10,000. So once a fluid has reached a Reynolds number greater than 10,000, it is considered as turbulent flow, right? And at turbulent flow, the power number is constant. So let's move on to question number 6. So this is a numerical. Um, so you have a large scale bioreactor with 10,000 liters of complex unit, and it has 10 to the power 4 per liter, and it is being sterilized. The del factor value for the system is 50, and you have been given the following information. A gas constant which is 1.987 cal per mole per Kelvin, and the temperature of 0 degree Celsius is 273.15 Kelvin. Okay. So now you have to find the probability of successful sterilization. And notice in this case that the temperature they have mentioned is 0 degree. No other temperature is being given to you. Okay. 0 degree Celsius. So that is the temperature that you have to take. So you know that the total number of pores, which is n naught, is equal to 10 to the power 4 pores per liter. And since you have 10,000 liters of media, so you multiply this 10 to the power 4 into 10,000 and you get a value of 10 to the power 8 force. So in the total system of 10,000 liters, you have 10 to the power 8 force. You know that the del factor is being given as 50, and del factor is also equal to the rate constant of depth into time. Okay. So you are assuming that all the viable cells or spores are identical, that is, they are identical in the sense that they will be equally affected by the sterilization. So the probability of extinction of the total population, which is P naught T, is given by 1 minus PT and to the total power of N naught. Okay. Where PT is the probability that an individual will still be viable at time t, which is where you are seeing the total number of cells, and N naught is the initial number of spores present. Okay. You're assuming that since it is not given to you, you're assuming that this is the first order death model. Okay. And you know that P peak, which is the probability that an individual will be viable at time t, is equal to e to the power of kd. Right? So now you have a formula for Cp. You can substitute it here in this formula, and you get P naught T is equal to 1 minus e to the power k dt, and this total expression is e to the power of n naught. So you know all these details. You know the value of E, you know the value of k dt, which is the del factor, which is T, and n naught, which is 10 to the power 8. Right? So once you substitute that value, you will get an answer of 5.18 into 10 to the power minus 4, which is the probability of extinction of force, which is also equal to the probability of a successful separation. You can see it's a very less probability. So at 0 degrees Celsius, you have a very less probability of successful sterilization. The next question then obviously would be the probability of unsuccessful separation. So you know that a probability is in total equal to 1. Right? All the options together is totally equal to 1. So 1 minus the probability of successful sterilization, which you have found here, will give you the probability of unsuccessful sterilization. So 1 minus 5.1 into 10 to the power minus 40 will give you an answer which is very much still closer to 1. So it is highly probable that the sterilization has been unsuccessful, since the value is very much closer to 1. So let's move on to question number 7 in case you don't have a doubt. Uh, the information given to you is that the media is to be bag sterilized in a 200-liter fermenter before it is used to grow microorganisms. Using 0.001 as the probability of a unsuccessful sterilization. In this case, since you see 0.001 is a small unit compared to 1, uh, and that is the probability of unsuccessful sterilization. So you know that the probability of successful sterilization is high. You have to ignore the heat up and cool down, okay? And the information given is for passive purothermophiles. So the number of poles is 1 into 10 to the power 8 poles per liter. The capital E value is given to you as 67.7 kilocal per mole. The value of A is given as 1 into 10 to the power 36.2 per minute, and R gas constant, which is the constant, is given as 1.987 cal per Kelvin per minute, and the temperature conversion unit is given as 0 uh, degree Celsius is equal to 273 Kelvin. You have to determine the rate constant of death in terms of R minus 1 and a temperature of 121 degrees Celsius. In this case, a temperature is given to you. So you know, according to our linear equation, Kb is equal to A small e to the power of capital E by RT, right? So all these values are known to you. So you know the value of A, which is 1 into 10 to the power 36.2 per minute. You know the value of E. You know the value of capital E, which is 67.7 into 10 to the power 3, because here the value is given to you in kilocal. So you have to convert that into cal. So that conversion is by multiplying it into 10 to the power 3. Okay, and you know the value of R, which is 1.987 cal per Kelvin per mole into the temperature. So you have to convert 121 degrees Celsius to Kelvin, and you do that by adding 273. Okay, so 121 plus 273 will give you the temperature in Kelvin. Okay, so as you go on solving this, you will get an answer of 0.00044 per minute, because the value of A is given in minutes, right? But the question is asking you to find the value in terms of per hour. So since it's per hour, since if it was when you convert per minute to per hour, you have to divide by 60, right? Since there is 60 minutes in an hour. But in this case, since it is per minute and you have to convert it into per hour, you multiply it by 60. Okay. You get a value of 2.64 per hour. So let's move on to the next question in case you don't have a doubt. So this is question number 8. So sterilization is being carried out for 1,000 cube pilot scale vessels. The media contains 10 to the power 6 organisms per centimeter cube. Okay. And the probability of unsuccessful sterilization is given as 1 in 1,000. So what you have to find is the del factor for this probability of contamination. So the number of viable cells at start of sterilization, that is N1, is 10 to the power 6. square, okay, into the 1000 dm cube, which is the scale of the vessel, but you have to convert it into centimeter cube because the amount of cell is given in centimeter per centimeter cube. Right? You have to convert this dm cube into centimeter cube. So for that you multiply it by 1000 because one decimeter is equal to 1000 centimeters. Okay? So you get the total number of viable cells at the start of sterilization by this. The number of viable cells at the end of sterilization, the data is given as 1 per 1000 is the remaining. So 1 per 1000 is 10 to the power minus 2. You know that the del factor is Kd into T, and you know that del factor is also natural log, that is ln of n1 by n2. So if you take natural log of n1, which is given in this way, by n2, you will get an answer of 34.5. So the del factor for this particular probability of contamination is 34.5. So now they are saying that during scale up, you have scaled up the dimension of the vessel from 1000 dm3 to 10,000 dm3 vessel, and the same media is being used. You have to now determine the del factor for the large vessel if the probability of the contamination is the same. Okay. So after scale up, the initial number of cells will change, right? So the amount of cells per centimeter cube will remain, but the volume of the vessel will change. So instead of 1000, as you would have seen here, it becomes 10,000. Okay, but the conversion unit remains the same. Again, to convert dm cube to centimeter cube, you multiply it by 1000. The number of viable cells at the end of sterilization is the same. It is 10 to the power minus 2. Okay. So again, to find the del factor, you use the formula ln n1 by n2, and you use the new n1 in this case. So the answer you get is 36.3. So once you increase the vessel size from 1000 dm cube to 10,000 dm cube, you see that the del factor changes from 34.5 to 36.2. Okay, so let's move on to the final question in this case. So question number 9. The media used for a bioprocess is contaminated with single cells with similar thermal response characteristics. Okay. It has been observed that by maintaining the media at 60 degrees Celsius for 15 minutes, 65% of the cells become non-viable. You have to determine the decimal reduction time, that is the time required for a certain amount of cells to decrease by a factor of 10 or a log factor of 1. Okay. So we know that the decimal reduction time is given by a formula of 2.303 by kg, which is the rate constant of them. And you know that for a first order reaction, the rate constant is given by this formula, which is 2.303 by T log 10 of initial number of cells by final number of cells. So these are all given to you. For you to find the decimal reduction time, you need only kd value. So let's figure out kd first. You know time is 15 minutes, and you have to convert that into seconds. Okay, so 15 minutes into 60 will give you 900 seconds. You don't know the exact initial cell, but you know that the reduction after 15 minutes is 65%. So you can assume that the initial volume, initial amount of cell was 100%. Right? So after 15 minutes, there is a reduction of 65%. So 100 minus 65, the remaining amount is 35%. Right? So you get the ratio. Okay. So KD is equal to 2.303 by 900 log 10 of 100 by 35. So you get KD as 0.00117. Okay. Now that you have KD, you can find out the decimal reduction time. So this D is 2.303 by 0.00117. Okay. And you find that the decimal reduction point in seconds is uh, 1968.38 seconds. And once you convert that into minutes by dividing it by 60, you get 32.80 minutes. So the decimal reduction time is 32.80. So for about 10,000 cells to you know, reduce to 1000, you need 32.80. That is what we need. Okay. So this is the final question. Do you have any doubts regards to this question or any of the questions in the assignment number 7?
No, ma'am.
All right, then that is all for today. I hope you understood.
Yes.
All right. Thank you so much.
Thank you, ma'am.